Está. Estaba muy alto la música. Vamos a estar viendo Odin Project. Bueno, bajé la música un toque. Miro por acá. Bueno, vamos a estar viendo estructura de datos y algoritmos comunes. Ok. Introducción.
so heartless, and you don't care. And I don't even know what I've been fighting for. You got me hoping, and you don't care. And I don't even know what I've been fighting for. Every time I fall in a deep, and I can't fight it, I can't fight it. You wreck my mind, I'm losing my sleep. watch the time pass us by. Is this feeling lying? Could you pass the lighter? Yeah, I'm trying to keep my cool. Nicotine in my veins, flaming up desires. What am I supposed to do? Cause it feels so good. Feeling wild like a zoo. Put me in a mood. Put me in a mood.
Welcome to this first course in the design and analysis of algorithms. I imagine many of you are already clear on your reasons for taking this course, but let me begin by justifying the course's existence and giving you several different motivations for learning about algorithms. So what is an algorithm? Well, we're not going to be needing a precise definition in this course, but essentially an algorithm is a well-defined set of rules, a recipe in effect, for solving some kind of computational problem. So for example, maybe you're given a bunch of numbers and you want to rearrange them into sorted order. Maybe you're given a road network with an origin and a destination and you want to compute the shortest path from point A to point B. Maybe you're given a bunch of tasks with deadlines and you want to know whether or not it's feasible to accomplish all of those tasks by their respective deadlines. So why study algorithms? Well, first of all, understanding the field of algorithms and also the related field of data structures is crucial for doing serious work in pretty much any other branch of computer science. That's the precise reason why, here at Stanford University, this is the course that's required for all of the degrees that the computer science department grants. Be it a bachelor's, a master's, or a PhD degree, we insist that you have mastery of the field of algorithms. So what are some examples of uses in the rest of computer science? Well, if you're doing routing in a communication network, that piggybacks on classical shortest path algorithms. The effectiveness of public key cryptography really rests on that of number theoretic algorithms. In, say, computer graphics, you need the computational primitives that are supplied by the study of geometric algorithms. Database indices rely on balanced search tree data structures, as covered in this course. And computational biology uses dynamic programming algorithms to measure the similarity among genomes. And the list goes on and on. A second reason to study algorithms is that they play a key role in modern technological innovation. Obviously, I could give any number of examples here. Let me just state one super obvious one, which is that search engines use a tapestry of algorithms to efficiently compute the relevance of various web pages. The most famous such algorithm, which you may have heard of, is the PageRank algorithm in use by Google. Indeed, in a December 2010 report to the United States White House, the President's Council of Advisors on Science and Technology argued that, in many areas, performance gains due to improvements in algorithms have vastly exceeded even the dramatic performance gains due to increased processor speed, as you'd be familiar with in the form of Moore's Law. Third, although this is getting significantly outside the scope of this course, algorithms are increasingly being used to provide a novel lens on processes outside of computer science and technology. For example, the study of quantum computation has provided a new and computational viewpoint on quantum mechanics. Price fluctuations in economic markets can be fruitfully viewed as an algorithmic process, and even evolution can be usefully thought of as a surprisingly effective search algorithm. The last two reasons I'm going to give you might sound a little flippant, but I think there's more than a grain of truth to both of them. Now, I don't know about you, but back when I was a student, my favorite classes were always challenging classes, but after I struggled through them, I somehow felt like I had a few more IQ points than when I started. So I hope this course provides a similar experience for many of you, that on the one hand, it's a bit of a struggle, you find the concepts challenging, but perhaps you feel just a tinge smarter after we're done. Finally, I hope that by the end of the course, a constant fraction of you will agree with me that designing and analyzing algorithms is simply fun. It's an endeavor that requires a rare blend of creativity and precision, and it can certainly be frustrating at times, but even more than that, it is addictive. So let's now descend from these lofty generalities and get much more concrete. And also, let's remember that we've all been learning and using algorithms since we were little kids. So once upon a time, in roughly third grade or so, you learned how to multiply two numbers. Now, you probably weren't thinking in these terms at the time, but multiplying two numbers is certainly a well-defined computational problem, and that procedure you learned back in third grade or so is indeed an algorithm. So let's just make that a little bit more precise. In this computational problem, we're given as input two numbers, let's say with n digits. And to make things interesting, why don't you think about n as being really quite large, say in the thousands. Maybe we're implementing an algorithm that's going to be used in a cryptography application where you need to keep track of really quite large numbers. So if we call the two input numbers x and y, The problem is simply to compute their product, x times y. So a quick digression. I'll certainly be the first to admit that my handwriting is not the greatest. I got a C in penmanship back in elementary school, and I think the teacher was being a little generous. But it's an acquired taste, but trust me, you will get used to it. Okay, back to integer multiplication. Now, when we talk about procedures for multiplying two numbers, we're going to be interested in counting how many steps are required in order to execute the multiplication. So how do we count a step? We'll talk more about this later, but for multiplying two numbers, let's just call a step the addition or multiplication of two single-digit numbers. So let's review the integer multiplication algorithm that we learned back in grade school just by working through a concrete example. Specifically, let's think of n equal 4, so let's look at two 4-digit numbers. Let's say 5, 6, 7, 8, and 1, 2, 3, 4. Now, as you'll recall, the procedure we learned way back when was just to take each digit of the bottom number and multiply it by each of the top numbers, and then to take each of those n partial products and add them up. So for example, you start with the 4, you multiply it by 8, you get 32, carry the 3, 4 times 7 is 28, add the 3, you get 1, carry the 3, and so on. So that gives you this first partial product, 22, 7, 12. Then you do a shift, so you effectively put a 0 in this final digit, and you repeat that procedure using the next digit, the 3. So again, 3 times 8 is 4, carry the 2, and so on. And you compute the final two partial products using the 2 and the 1. And having computed all of the partial products, you just add them up to get the final product. Now the question I'm interested in is how much work, how many primitive operations did we do to multiply these two numbers, and more generally, how many does it require to multiply two n-digit numbers as a function of n? Well, just to get sort of a ballpark viewpoint for what's going on, we started with two n-digit numbers, and at the end of the day, we basically filled out a grid of size roughly n by n, give or take a little bit. So just in ballpark terms, it seems that multiplying two n-digit numbers required essentially a quadratic number of operations, a small number of operations to fill in each entry in this grid. The grid is n by n, roughly, so that's roughly n squared operations. In a little more detail, we could look at each of the partial products separately. So to compute, say, this first partial product, what did we do? We took the 4, we multiplied it by each of the n digits on top. We also did some carries, so that affects things a little bit. But in the end, we did somewhere between, say, n and 2n primitive operations to compute this first partial product. And that's true, of course, for each of the n partial products. So that's roughly n operations for each of the n partial products. So that's roughly n squared operations to compute all of the partial products. Then we have to add it all up at the end, but that takes just an extra number of constant times n primitive operations to do all of those additions. So summarizing, overall, the number of primitive operations required to multiply two n-digit numbers using this procedure grows quadratically with the length n. So for example, if you double the length of two numbers, you expect to do roughly 4 times as many primitive operations if you use this iterative algorithm for multiplying two numbers. Now, depending on what type of third grader you were, you might well have accepted this procedure as being the unique, or at least the optimal way of multiplying two n-digit numbers together. And if you want to be an expert algorithm designer, that kind of obedient attitude is something you're going to have to learn to discard. Here's a favorite quote of mine. It's from a quite early textbook in the field, The Design and Analysis of Computer Algorithms by A.O. Hopcroft and Ullman. And after highlighting a number of algorithmic design techniques, they conclude by saying, perhaps the most important principle for the good algorithm designer is to refuse to be content. So that's a beautifully accurate quote. I might rephrase it more succinctly by just saying, if you want to be a good algorithm designer, you should adopt the following mantra. You should always be asking, can we do better? This is a particularly appropriate question to ask when you're faced with some kind of naive or obvious algorithm for solving a problem like the third grade algorithm for integer multiplication. But this will come up over and over again. We'll see an algorithm, there'll be an obvious solution, but with some extra algorithmic ingenuity, by detecting subtle structure in the problem, we'll be able to do significantly, qualitatively better than the naive or the obvious solution to the problem. So let's apply this cocky attitude to the problem of multiplying two integers. Let's just suppose as a working hypothesis that there is some procedure which is better than what we learned back in elementary school. What could it possibly look like? So as someone with some programming experience, you know that there are not only iterative algorithms, iterative programs, like the one we just outlined for multiplying two integers, but there are also recursive programs. These are programs that call themselves, typically on an input of a similar form, but with smaller size. So as a working hypothesis, let's imagine that there's some interesting recursive approach to multiplying two integers. What must such an algorithm look like? Well, it must somehow fundamentally involve calling itself on smaller problems, that is, on smaller numbers, numbers with fewer digits. So what kind of decomposition on numbers could we use to enable this kind of recursive approach? Well, if you think about it, there's a pretty natural way to break a number with a bunch of digits into a couple numbers with fewer digits. Namely, just take the first half of the digits, the first n over 2 digits, regard that as a number in its own right, and the second half of the digits, regard that as a number in its
own. Sorry, estoy viendo un mensaje. How we say catchy. Catchy. No.
element inside of an array. Unlike linear search, it requires a special condition be met beforehand, but it's so much more efficient if that condition is in fact met. So what's the idea here? It's divide and conquer. We want to reduce the size of the search area by half each time in order to find a target number. This is where that condition comes into play, though. We can only leverage the power of eliminating half of the elements without even looking at them if the array is sorted. If it's a complete mix-up, we can't just out of hand discard half of the elements because we don't know what we're discarding. But if the array is sorted, we can do that because we know that everything to the left of where we currently are must be lower than the value we're currently at, and everything to the right of where we are must be greater than the value we're currently looking at. So what's the pseudocode steps for binary search? You repeat this process until the array, or as we proceed through, subarrays, smaller pieces of the original array, is of size 0. Calculate the midpoint of the current subarray. If the value you're looking for is in that element of the array, stop, you found it. That's great. Otherwise, if the target is less than what's at the middle, so if the value we're looking for is lower than what we see, repeat this process again, but change the endpoint, instead of being the original complete full array, to be just to the left of where we just looked. We knew that the middle was too high, or the target was less than the middle, and so it must exist, if it exists at all in the array, somewhere to the left of the midpoint. And so we'll set the array location just to the left of the midpoint as the new endpoint. Conversely, if the target is greater than what's at the middle, we do the exact same process, but instead we change the start point to be just to the right of the midpoint we just calculated. And then we begin the process again. Let's visualize this, OK? So there's a lot going on here, but here's an array of 15 elements, and we're going to be keeping track of a lot more stuff this time. So in linear search, we were just caring about a target, but this time we want to care about where are we starting to look, where are we stopping looking, and what's at the midpoint of the current array. So here we go with binary search. We're pretty much good to go, right? I'm just going to put down below here a set of indices. This is basically just what element of the array we're talking about. With linear search, we care in as much as we need to know how many elements we're iterating over, but we don't actually care what element we're currently looking at. In binary search, we do, and so those are just there as a little guide. So we can start, right? Well, not quite. Remember what I said about binary search? We can't do it on an unsorted array, or else we're not guaranteeing that the certain elements or values aren't being accidentally discarded when we just decide to ignore half of the array. So step 1 with binary search is you must have a sorted array. And you can use any of the sorting algorithms we've talked about to get you to that position. So now we're in a position where we can perform binary search. So let's repeat the process step by step and keep track of what's happening as we go. So the first thing we need to do is calculate the midpoint of the current array. Let's say, first of all, we're looking for the value 19. We're trying to find the number 19. The first element of this array is located at index 0, and the last element of this array is located at index 14. And so we'll call those start and end. So we calculate the midpoint by adding 0 plus 14 divided by 2, pretty straightforward midpoint. And we can say that the midpoint is now 7. So is 15 what we're looking for? No, it's not. We're looking for 19. But we know that 19 is greater than what we found at the middle. So what we can do is change the start point to be just to the right of the midpoint and repeat the process again. And when we do that, we now say the new start point is array location 8. What we've effectively done is ignored everything to the left of 15. We've eliminated half of the problem. And now instead of having to search over 15 elements in our array, we only have to search over 7. So 8 is the new start point. 14 is still the end point. And now we go over this again. We calculate the new midpoint. 8 plus 14 is 22. Divided by 2 is 11. Is this what we're looking for? No, it's not. We're looking for a value that's less than what we just found. So we're going to repeat the process again. We're going to change the end point to be just to the left of the midpoint. So the new end point becomes 10. And now that's the only part of the array we have to sort through. 2 is 11. Is this what we're looking for? No, it's not. We're looking for a value that's less than what we just found. So we're going to repeat the process again. We're going to change the end point to be just to the left of the midpoint. So the new end point becomes 10. And now that's the only part of the array we have to sort through. So we have now eliminated 12 of the 15 elements. We know that if 19 exists in the array, it must exist somewhere between element number 8 and element number 10. So we calculate the new midpoint again. 8 plus 10 is 18, divided by 2 is 9. And in this case, look, the target is at the middle. We found exactly what we were looking for. We can stop. We've successfully completed a binary search. All right, so we know this algorithm works if the target is somewhere inside of the array. Does this algorithm work if the target is not in the array? Well, let's start it again, and this time let's look for the element 16, which visually we can see does not exist anywhere in the array. The start point is again 0. The end point is again 14. Those are the indices of the first and last elements of the complete array. And we'll go through the process we just went through again, trying to find 16, even though visually we can already tell that it's not going to be there. We just want to make sure that this algorithm will in fact still work in some way and not just leave us stuck in an infinite loop. So what's the step first? Calculate the midpoint of the current array. What's the midpoint of the current array? Well, it's 7, right? 14 plus 0 divided by 2 is 7. Is 15 what we're looking for? No, it's pretty close, but we're looking for a value slightly bigger than that. So we know that it's going to be nowhere to the left of 15. The target is greater than what's in the midpoint, and so we set the new start point to be just to the right of the middle. The midpoint is currently 7, so let's say the new start point is 8. And what we've effectively done again is ignored the entire left half of the array. Now we repeat the process one more time. Calculate the new midpoint. 8 plus 14 is 22. Divided by 2 is 11. Is 23 what we're looking for? Unfortunately, no. We're looking for a value that is less than 23. And so in this case, we're going to change the end point to be just to the left of the current midpoint. The current midpoint is 11. And so we'll set the new end point for the next time we go through this process to 10. Again, we go through the process again. Calculate the midpoint. 8 plus 10 divided by 2 is 9. Is 19 what we're looking for? Unfortunately, no. We're still looking for a number less than that. So we'll change the end point this time to be just to the left of the midpoint. The midpoint is currently 9, so the end point will be 8. And now we're just looking at a single element array. What's the midpoint of this array? Well, it starts at 8, it ends at 8. The midpoint is 8. Is that what we're looking for? Are we looking for 17? No, we're looking for 16. So if it exists in the array, it must exist somewhere to the left of where we currently are. So what we're going to do? Well, we'll set the end point to be just to the left of the current midpoint. So we'll change the end point to 7. Do you see what just happened here, though? Look up here now. Start is now greater than end. Effectively, the two ends of our array have crossed. And the start point is now after the end point. Well, that doesn't make any sense, right? So now what we can say is we have a subarray of size 0. And once we've gotten to this point, we can now guarantee that the element 16 does not exist in the array because the start point and end point have crossed. And so it's not there. Now notice that this is slightly different than the start point and end point being the same. If we had been looking for 17, it would have been in the array. And the start point and end point of that last iteration before those points crossed, we would have found 17 there. It's only when they cross that we can guarantee that the element does not exist in the array. So this took a lot fewer steps than linear search. In the worst case scenario, we had to split up a list of n elements repeatedly in half to find the target, either because the target element will be somewhere in the last division, or it doesn't exist at all. So in the worst case, we have to split up the array, do you know? Log of n times. We have to cut the problem in half a certain number of times. That number of times is log n. What's the best case scenario? Well, the first time we calculate the midpoint, we find what we're looking for. In all of the previous examples on binary search we've just gone over, if we had been looking for the element 15, we would have found that immediately. That was at the very beginning. That was the midpoint of the first attempt at a split of a division in binary search. And so in the worst case, binary search runs in log n, which is substantially better than linear search in the worst case. In the best case, binary search runs in omega of 1. So binary search is a lot better than linear search, but you have to deal with the process of sorting your array first before you can leverage the power of binary search. I'm Doug Lloyd. This is CS50.
Muy interesante. Pero claro, el array tiene que estar ordenado. Si no está ordenado, Se puede proceder. Mm.
In some past videos, I've talked about binary search trees and how to put them together. However, I took a data set that was very well structured, and so the tree was nice and balanced. And then in some of our other videos, we went over red-black trees and how to balance a tree that wasn't really structured the way you'd want a red-black tree to be structured. In this video, I'm going to show you how you can take an array and how you create or construct a binary search tree based on the elements of that array in their original order. So you can see on the right hand side here, we have an array with elements 5, 7, 1, 15, 9, 2, 14, 8, 7, and 3. And so if we're going to create a binary search tree with this array, they have to actually go in order. And so I'm going to show you how that works. So the first element in our array is going to be 5. And so it's nice, easy. We create 5 and put it inside of the at the root node. The next one we're going to use is going to be 7, and because 7 is greater than 5, it'll do that comparison, and then it'll put 7 on the right hand side right next to 5. After that, we have a 1. 1 is less than 5, so it goes to the left, and right here we have a very nice basic tree structure. We have our root node. We have 1 being the item or the node to the left, 7 to the right. So far everything is normal. Now we're going to add 15. 15 is greater than 5. It's greater than 7, so it needs to go all the way to the right. Now I'm just going to start adding some more in order in the array. So we'll go 5, 7, 15. Now 9 is less than 15, and so we put it there on the left. Now if you are familiar with red-black trees or some of these more self-balancing trees, you would know that this is not the way this would have been constructed. It would have rebalanced itself and would have swapped out the 9 right here, so the 9 would be connected to the 5, the 7 would be on the left hand side, 15 on the right hand side. However, this is just a regular binary search tree, so we have to treat it as such, and we have to add the elements in order. And this is the reason why people created things like red-black trees, was because as you'll see here in a minute, this tree is gonna look pretty odd in a short period of time. So next element is 2. 2 is less than 5, so we know it goes to the left. It's greater than 1, so we'll get pulled over into the right. Then we're going to add 14. It's greater than 5, greater than 7, but less than 15, so it's going to move to the left. And it's greater than 9, so you'll see that moves all the way to the bottom of our binary search tree. So we have 14, we have just 3 elements left. We have 8. It's going to traverse the tree. We see that it's greater than 7, but less than 15, and less than 9. And our second to last one is 7. Now that 7 is an interesting one, because you can see that it is greater than 5. It's actually equal than 7, but because it's equal to 7, it's not less than 7. It gets moved. It goes to the right. It's less than 15, less than 9, less than 8, and it goes right here. So even though these two nodes are actually the same value, one is directly a descendant of the root node, and the other one is all the way here. Now it is the closest node to this 7 because they are equal, and so it's neat to see the way that that automatically happens, but it's still pretty important to see that you can have a tree that is structured like this if you take everything in order. And the last one we're going to do is a 3, and that's greater than 1, greater than 2, so it gets pulled here. And so given this data structure here on the right hand side, this is what a visual representation of the tree would look like. So you can see it's not balanced, however, it is properly structured. If you were to run a search on this, so say that we wanted to find 8. So if we want to find 8, it'll go to 5, 7, 15. It's less than 15, so it knows to look to the left. It's less than 9. And there it is. That it found the element. So this is how you construct a binary search tree given an array.
Esto es lo que vi recién. Sí.
And side right next to 5.
About the principle of queue and stacks, which are concepts used in breadth first search and depth first search, respectively, by watching this video. Okay.
In computer science, data structures are ways to store and organize data so it can be used efficiently. Knowing about data structures is important because picking the right one can dramatically affect the performance of a program. Let's look at two of the simplest data structures, stacks and queues. First, stacks. The word stack in computer science is used a lot like it is in English, so let's think of a stack of books. If you want to add a book to the stack, you'll add it to the top. And if you want to get a book from the stack, you'll start from the top as well and remove elements. It's cumbersome to access a book in the middle of the stack, so we generally avoid that. A stack has a top and a bottom, and we can add and remove only from the top. In computer science, we tend to talk about pushing elements onto the top of a stack for adding, and popping elements from the top of a stack for removing. So a stack is a data structure in which elements are sorted by insertion order. The last element that you put in is the first one that's going to come out. Elements have no index, so we can't access them in the middle of the stack. We can only add to the top and remove from the top, pushing and popping. Stacks are useful in contexts in which we want to reverse the order of elements. For example, think about the undo button in a lot of applications. The application stores activities performed in a stack. And so when you press the undo button, the activity that's undone is the last one that was performed. Now let's look at queues. The word queue is not used in American English very often, but in British English it means a single file line. So let's think about a line at a movie theater. So somebody starts the line and additional people may join after the first person. And the first person to get help will be the first person who joined the line. So queues have a front and a back. And we can add elements to a queue only from the back, and we can remove elements only from the front. In computer science, we might talk about adding as enqueuing and removing as dequeuing. Just like in stacks, elements in queues don't have indexes, so we can't access them directly. Again, think about the movie theater line example. The person working at the theater can't just ask the person in the red shirt to come and be helped. The patrons get helped in order. So a queue is a data structure in which, just like stacks, elements are sorted by insertion order. However, in queues, the first element that you put in is the first one that comes out. Again, elements have no indexes, so we can't access an element in the middle of a queue. We can only add to the back and remove from the front. Queues are useful in contexts when we're managing resources. For example, think of a print queue. If we have many people in an office sending jobs to the same printer, the first person who sends a job to the printer gets their job first. Similarly, if we have a website and several people are accessing that website, the first person who tries to access it is the first person who gets the page back.
Ok. Finalmente, first search and did first. Okay.
In this lesson, we are going to talk about binary tree traversal. When we are working with trees, we may often want to visit all the nodes in the tree. Now, tree is not a linear data structure like array or linked list. In a linear data structure, there would be a logical start and a logical end. So we can start with a pointer at one of the ends and keep moving it towards the other end. For a linear data structure like linked list, for each node or element, we would have only one next element. But tree is not a linear data structure. I have drawn a binary tree here. Data type is character this time. I filled in these characters in the nodes. Now for a tree, at any time, if we are pointing to a particular node, then we can have more than one possible directions. We can have more than one possible next nodes. In this binary tree, for example, if we will start with a pointer at root node, then we have two possible directions. From F, we can either go left to D or we can go right to J. And of course, if we will go in one direction, then we will somehow have to come back and go into the other direction later. So tree traversal is not so straightforward, and what we are going to discuss in this lesson is algorithms for tree traversal. Tree traversal can formally be defined as the process of visiting each node in the tree exactly once in some order. And by visiting a node, we mean reading or processing data in the node. For us in this lesson, visit will mean printing the data in the node. Based on the order in which nodes are visited, tree traversal algorithms can broadly be classified into two categories. We can either go breadth first or we can go depth first. Breadth first traversal and depth first traversal are general techniques to traverse or search a graph. Graph is a data structure, and we have not talked about graph so far in this series. We will discuss graph in later lessons. For now, just know that tree is only a special kind of graph. And in this lesson, we are going to discuss breadth first and depth first traversal in context of trees. In a tree, in breadth first approach, we would visit all the nodes at same depth or level before visiting the nodes at next level. In this binary tree that I'm showing here, this node with value f, which is the root node, is at level 0. I'm writing L0 here for level 0. Depth of a node is defined as number of edges in path from root to that node. A root node would have depth 0. These two nodes D and J are at depth 1. So we can say that these nodes are at level 1. Now these 4 nodes are at level 2. These 3 nodes are at level 3. And finally this node with value H is at level 4. So what we can do in breadth first approach is that we can start at level 0. We would have only one node at level 0, the root node. So we can visit the root node. I'll write the value in the node as I'm visiting it. Now level 0 is done. Now I can go to level 1 and visit the nodes from left to right. So after F, we would visit D, and then we would visit J. And now we are done with level 1. So we can go to level 2. We will go like B, then E, then G, and then K. And now we can go to level 3, A, C, and I, and finally I can go to level 4. This kind of breadth first traversal in case of trees is called level order traversal. And we will discuss how we can do this programmatically in some time. But this is the order in which we would visit the nodes. We would go level by level from left to right. In breadth first approach, for any node, we visit all its children before visiting any of its grandchildren. In this tree, first we are visiting F, and then we are visiting D, and then we are not going to any child of D like B or E along the depth. Next we are going to J. But in depth first approach, if we would go to a child, we would complete the whole subtree of the child before going to the next child. In this example tree here, from F, the root node, if we are going left to D, then we should visit all the nodes in this left subtree. That is, we should finish this left subtree in its complete depth. Or in other words, we should finish all the grandchildren of F along this path before going to right child of F, J. And once again, when we will go to J, we will visit all the grandchildren along this path. So basically, we will visit the complete right subtree. In depth first approach, the relative order of visiting the left subtree, the right subtree, and the root node can be different. For example, we can first visit the right subtree, and then the root, and then the left subtree. Or we can do something like we can first visit the root, and then the left subtree, and then the right subtree. So the relative order can be different, but the core idea in depth first strategy is that visiting a child is visiting the complete subtree in that path. And remember, visiting a node is reading, processing, or printing the data in that node. Based on the relative order of left subtree, right subtree, and the root, there are three popular depth first strategies. One way is that we can first visit the root node, then the left subtree, and then the right subtree. Left and right subtrees will be visited recursively in same manner. Such a traversal is called pre-order traversal. Another way is that we can first visit the left subtree, then the root, and then the right subtree. Such a traversal is called in-order traversal. And if root is visited after left and right subtrees, then such a traversal is called post-order traversal. In total, there are 6 possible permutations for left, right, and root, but conventionally, a left subtree is always visited before the right subtree. So these are the 3 strategies that we use. Only the position of root is changing here. If it's before left and right, then it's pre-order. If it's in between, it's in order. And if it's after left and right subtrees, then it's post-order. There is an easy way to remember these 3 depth first algorithms. If we can denote visiting a node or reading the data in that node with letter D, going to the left subtree as L and going to the right subtree as R. So if we can say D for data, L for left, and R for right, then in pre-order for each node we will go DLR. First we will read the data in that node, then we will go left, and once the left subtree is done we will go right. In order traversal, first we will finish the left subtree, then we will read the data in current node, and then we will go right. In post order, for each node first we will go left, once left subtree is done we will go right, and then we will read the data in current node. So pre-order is data left right, in order is left data right, and post order is left right and then data. Pre-order, in-order, and post-order are really easy and intuitive to implement using recursion, but we will discuss implementation later. Let's now see what will be the pre-order, in-order, and post-order traversal for this tree that I've drawn here. Let's first see what will be the pre-order traversal for this binary tree. We need to start at root node, and for each node we first need to read the data, or in other words visit that node. In fact, instead of DLR we could have said VLR here, V for visit. We can use any of these assumptions, V for visit or D for data. I will go with DLR here. So let's start at the root. For each node we first need to read the data. I'm writing F here, the data that I just read. And now I need to go left and finish the complete left subtree. And once all the nodes in the left subtree are visited, then only I can go to the right subtree. The problem here is actually getting reduced in a self-similar or recursive manner. Now we need to focus on this left subtree. Now we are at D, root of this left subtree of F. Once again, for this node we will first read the data, And now we can go left. We will go towards E only when these three nodes A, B, and C will be done. Now we are focusing on this subtree comprising of these three nodes. Now we are at B, we can read the data, and now we can go left to A. There is nothing in left of A, so we can say that for A, left subtree is done, and there is nothing in right as well, so we can say right is also done. Now for B, left subtree is done, so we can go right to C and left.
Hola Jerónimo, saludos. ¿Cómo va? ¿Todo bien?
And right of C are null. And now for D, left subtree is done, so we can go right. Once again for E, left and right are null. And now at this stage for F, complete left subtree is visited, so we can go right. Now we need to go left of J, and there is nothing in left of G, so we can go right. And now we can go left of I. For H, there is nothing in left and right. Now at this stage left subtree of I is done and right subtree is null. And now we can go back to J. The left subtree for J is done, so we can go to its right subtree. Finally we have K here, and we are done with all the nodes. This is how we can perform a pre-order traversal manually. Actual implementation would be a simple recursion, and we will discuss it later. Let's now see what will be the in-order traversal for this binary tree. In in-order traversal, we will first finish visiting the left subtree, then visit the current node, and then go right. Once again we will start at the root and we will first go left. Now we will first finish this subtree. Once again for D, we will first go left to B, and from B we will go to A. Now for A, there is nothing in left, so we can say that for this guy left subtree is done, so we can read the data. And now we can go to its right, but there is nothing in right as well, so this guy is done. Now for B, left subtree is done, so we can read the data. And now for B we can go right. For C, once again there is nothing in left, so we can read the data, and there is nothing in right as well. Now left of D is completely done, so we can visit it, read the data here. Now we can go to its right to E. For E, once again left and right are null. At this stage left subtree of F is done, so we can read the data, and now we can go to right of F. If we will go on like this, this finally will be my in-order traversal. This tree that I'm showing here is actually a binary search tree. For each node, the value of nodes in left is lesser and the value of nodes in right is greater. So if we are printing in this order, left subtree and then the current node and then the right subtree, then we would get a sorted list. In-order traversal of a binary search tree would give you a sorted list. Okay, now you should be able to figure out the post-order traversal. This is what we will get for post-order traversal. I leave it for you to see whether this is correct or not. I'll stop here now. In next lesson we will discuss implementation of these tree traversal algorithms. Thanks for watching.
Cool. Muy interesante lo de los árboles binarios. Bro, ¿qué me recomiendas el estudiar en Odin? Yo ayer empecé, estoy haciendo la sección de JavaScript. ¿Qué estás haciendo ¿Ya pasaste la parte de Foundations? ¿De fundamentos? ¿O recién estás empezando? Ah, recién empezaste, estás acá en la parte de los fundamentos. Claro, estás en esta parte, en Foundations. Estaba en la parte donde mostraban todos los tipos de código en HTML y eso. Ah, acá estarás. La parte de HTML, fundamentos de HTML. Sí, debe estar acá en esta parte, estás seguro. Sugerencia, si te llevas bien con el inglés y tenés buen manejo del inglés, quédate, quédate con solamente un recurso. No hagas como yo de ir probando todo porque al final nunca vas a terminar de, de quedarte con solo curso. Por lo menos recomiendan eso y tienen razón. Yo empecé con Bootcamps, hice todo hasta JavaScript y después me pasé a Odin. Porque bueno, no lo conocía Odin o lo había visto pero no lo había hecho. Pero sí, yo diría que te apegues a un solo recurso y trates de completarlo. Porque si no caes en lo que le dicen el tutorial hell, que siempre estás haciendo curso y nunca estás dando vueltas sobre lo mismo y nunca estás avanzando. Y bueno, tiene sentido. Pero sí, es cuestión de quedarse, porque el recurso está lleno de recursos. Bueno, acá tenés a JavaScript, fundamentos. Yo estoy tratando de hacer eso. De terminar de Odin Project. Pero bueno, como te digo, a mí me gusta investigar y actualmente estoy haciendo esto, le estoy tratando de dedicar el mayor tiempo posible a esto. Pero estoy en un bootcamp yankee de Estados Unidos. Iba a hablar de eso sobre en el canal, pero bueno, como lo cerraron para el resto del mundo no tiene sentido. Pero bueno, tuve la suerte de poder ingresar y bueno, lo que estamos haciendo ahora es... bueno, son dos conceptos de justamente HTML, CSS, JavaScript y algo de Ajax. Lo bueno que tiene esto es que te dan como una pasantía. Siempre y cuando te elijan. Si te eligen para esa pasantía, es una pasantía paga. Así que más que nada por eso estoy en el bootcamp ese. Pero ya te digo, haciendo Odin Project, ni siquiera por ahí terminarlo, pero porque no sé si estás en el Discord de Odin Project, te lo recomiendo. Está buenísimo lo que cuenta la gente de cómo han hecho su ruta y las historias, ¿no? La verdad que está genial. Sí, olvídate. Por eso, o sea, en realidad es medio larga la historia. o- em, no, de nada, gracias por pasar. El bootcamp se llama Code the Dream. Si lo querés chusmear, ese es el bootcamp. Pero bueno, como te digo, cerraron las inscripciones para todo el mundo. Porque son una comunidad chiquita. Imagínate que que tenían alumnos, por ejemplo, 15 alumnos por cohorte, por camada, ¿no? Y enseñan también introducción a la programación, algo de, bueno, tenés Ruby y tenés Node y tenés ves en React. Así que vos podés cursar todo o solamente lo que te interesa. Lo bueno que tienen es que, ya te digo, vos aplicás, después de cursar tenés una práctica de 2 meses y medio para simular el trabajo en equipo con tus compañeros y desarrollan algún proyecto sencillo, algo para la comunidad. Es una comunidad para ir para Carolina del Norte. Algo simple que necesiten, bueno, lo desarrollas con tus compañeros y eso te sirve para ponerlo en tu portfolio, por ejemplo. Y es un proyecto real que tiene una utilidad para la gente, ¿no? Y eso te suma, ¿no? Pero después de eso vos podés aplicar a le dicen internship, que es una pasantía, con ellos, con los del bootcamp. Y bueno, también tenés que llenar un formulario, explicar y qué sé yo, por qué te tienen que elegir y qué sé yo, que no sé cuánto. Pero si quedás elegido, tenés una pasantía paga por como mínimo de 9 meses y como máximo de un año. Son alrededor de 35.000 dólares al año. Em, Así que imagínate, para nosotros, para la gente de Latinoamérica, es un buen dinero. Pero como te comentaba, se sumó bastante gente a mitad de año. Imagínate, tenían alumnos de, no sé, 30 alumnos como máximo por cursada y ahora eso tienen 260 alumnos, casi 300 alumnos por cursada, así que explotó bastante, ¿no? Eh, bueno, por eso lo cortaron ahora. Bueno, yo tuve la suerte, gracias, de poder acceder al bootcamp, gracias a un amigo que me comentó, que la verdad que no tenía ni idea. Y bueno, entré y lo estoy cursando y lo voy a seguir a muerte porque ya te digo, me interesa mucho lo de la pasantía, ¿viste? Eh, y eso también, bueno, me va a servir para ponerlo como experiencia en mi currículum. Muy interesante. Te lo muestro. Te muestro la página para que la tengas presente. Este es el bootcamp. Em, Muy interesante. Tenés mentorías todas las semanas, en distintos horarios. Puedes hacer sesiones con desarrolladores seniors, uno a uno, o por ahí meterte en alguna sesión con tus compañeros, que generalmente son 3, 4. Y está bueno porque todos tienen la oportunidad de preguntar, sacarse las dudas. Los challenges, a medida que vas avanzando, tenés asignado ¿cómo es que se llama? Un code reviewer, que es un desarrollador que se enfoca en vos, en darte feedback sobre tus challenges que vas entregando. Y bueno, la verdad que está genial. Em, Tenerlo presente, porque por ahí vuelven a abrir las inscripciones y podés llegar a entrar. Em, bueno, si le das a apply te dice que no, porque Acá te da una bienvenida y demás. Acá aparece el formulario. Antes, cuando vos ponías, por ejemplo, dice vivís actualmente en Estados Unidos, en los territorios estadounidenses, si le ponías que sí, si le ponías que no, te dejaba para elegir, por ejemplo, Argentina, Colombia, qué sé yo. Ahora no, ¿ves? Ahora lo dice, lo lamentamos, pero no aceptamos solicitantes afuera de los Estados Unidos. Pero bueno, a tenerlo en cuenta para el futuro. Con esa guita me compro un Mustang, jaja, gracias. Voy a googlear y ver cómo ingresar. Se ve genial, pero cada año hacen inscripciones, ¿verdad? Ya te digo, anótatelo en codedream.org y estate atento porque ahora cerraron, porque yo digo, la cantidad de alumnos que tienen los superó bastante y son una comunidad chiquita, ¿viste? Em, pero bueno, mientras esperás a que se abra esto, yo diría que no esperes que sigas directamente con Odin Project y más o menos yo estoy tratando de dedicarle, iba a decir 4 horitas, pero siendo sincero le estoy dedicando entre 2 y 3 horitas por día y bueno, em, tampoco hay que apurarse, hay que tratar de asimilar bien los conceptos, seguir practicando. Qué sé yo, cada uno tiene su ritmo. Hay gente que estudia 8 horas por día y me parece genial y en 9 10 meses ya está buscando trabajo. Yo vengo desde el enero del año pasado estudiando, pero he estado probando distintos recursos. He estado en Bootcamps, estuve haciendo lo de Oracle One, después pasé por Odin, hice un parate en Odin y me puse a ver, no me acuerdo qué otro Open Bootcamp estuve haciendo. Y bueno, todo ese tiempo, si me hubiera enfocado solamente en Odin Project, quizás en un año hubiera estado listo para buscar trabajo. Un año o, no sé, 12 14 meses, una cosa así. Mm, pero bueno, todos recomiendan eso. Enfocarse en un recurso que te guste y darle para adelante. Por ejemplo, hay uno muy parecido que es App Academy, creo que es. Es muy parecido a The Odin Project. La única diferencia que tienen es que tienen, ¿cómo es que se llama? Videos. Vos podés ir leyendo y podés, tienen un montón de, qué sé yo, si te gusta más la parte visual, pero también tiene de todo. Incluso dicen que el contenido es mejor que Odin Project, pero bueno, tenés HTML, Git, bueno, recursión, eso es lo que estaba viendo. Pero ves, tenés texto como Odin, pero tenés videos. Em, depende de lo que te guste. Mirá, esto era un bootcamp que era pago, pero lo abrieron hace, no sé, hace un par de años, 1 o 2 años. Ya te digo, si te gusta más el contenido visual, ver videos, em, pasate por acá, por App Academy, y ahí te pego el link en el chat para que lo tengas. Em, y lo vas viendo, qué sé yo, está bueno también. Está, creo que está solamente, sí, solamente en inglés. Em, Muy interesante, la verdad. Y también, ojo, también tienen challenge. em, Yo te digo, lo estuve mirando por arriba, pero no, bueno, acá ves, no tienen... Es muy parecido porque te hace setear, por ejemplo, em, claro, depende si vos trabajás en Windows, Mac o Linux, te hace bajar, te hace bajar todo tu entorno de desarrollo, ¿no? Visual Studio Code y bueno, todo eso. O imagínate, acordate, este bootcamp era pago. Gente que pagaba, no sé, no me acuerdo cuánto pagaba, pero era un dinero en dólares. Y bueno, y lo abrieron y es uno de los mejores currículum que tienen, que están disponibles, ¿no? Imagínate que hay de todo. Tenés, bueno, los callbacks, recursión, TDD, esto no me acuerdo qué era. Programación orientada a objetos. ¿Qué más? Estructura de datos de algoritmo, que era lo que estaba viendo recién yo en Odin. Mirá, muy bueno. Árboles binarios, lo que estaba viendo recién. Graph. Estos también. Bueno, tenés Express. Bueno, ves que hice Optional Projects. Express y SQLize. React. Redux. Tenés una banda de estructura de datos. Flask. Mira. Docker y microservicios. Mm, bastante completo. Em, por ahí, si no te convence Odin Project, mandate acá que vas a tener bastante para entretener. Después, bueno, acá hay un montón de recursos. Tenés Full Stack Open, pero bueno, Full Stack Open yo lo quise probar y bueno, yo me choqué con una pared porque después leyendo me enteré que una vez que vos ya tengas experiencia, por ejemplo, en Odin Project, est- está bueno pasarse a Full Stack Open para reforzar conocimientos de todo lo que viste en Odin. Bueno, me queda para ver esto. Pero bueno, me parece que lo voy a ver. em, lo voy a ver luego. A ver cuánto dura cada uno. Para tener una idea más o menos de... Bueno, 11 minutos. 11 minutos por acá. Y este debe tener otro tanto, sí, perfecto. Así que tengo 25 minutos más o menos para terminar de ver eso. Em, bien. Mm, Khan Academy, esta es otra buena. Khan Academy tiene también tiene cosas muy interesantes. Bueno, yo hice esto, pero tenés cursos. Pero la verdad es abrumadora la información que hay en internet. Yo al enterarme de Bootcamps y Odin casi me volví loco, jaja, no sabía por dónde empezar después. Claro, es terrible, es impresionante la cantidad que hay. Em, si te llevas bien con el inglés, te vuelvo a recomendar Odin Project o App Academy. Pero elegí uno y centrate en ese. Quédate con ese solo. Y terminalo, y terminalo. Así te lleve 2 años. Yo estoy, como te digo, hace un año y medio. Y, pero bueno, nada, hay que mentalizarse y elegir un recurso que te guste y darle para adelante. Darle para adelante. Lo que pasa es que la diferencia de Free Cam es como que te va llevando de la mano. En Odin Project es más real. Porque vos cuando estés trabajando no vas a tener a tu colega y te decir, bueno, hace esto, a no ser que le pidas ayuda, ¿no? Pero vas a tener que investigar mucho por tu cuenta. Te lo digo porque tengo amigos desarrolladores afuera, dos en realidad, dos amigos, y, y se la pasan investigando y usando mucho ChatGPT para hacer cosas sencillas y qué sé yo, así que Odin Project te plantea un escenario más real. Porque te hace, por ejemplo, instalar Linux. Si estás en Windows, no es que tenés que ahorrar Windows, sino que puedes instalar una máquina virtual y ahí adentro instalar Linux y trabajar todo desde adentro. Aunque como ves, yo estoy haciendo Odin Project, pero estoy en Windows, estoy usando Windows 10. Em, por ahí, si revisas mi canal, los primeros videos que hice sobre FreeCodeCamp o sobre Odin Project vas a ver que estoy usando Linux. Em, pero bueno, cada uno tiene sus gustos. Pero sí, la información es impresionante. Te das cuenta que em, no es como que te lo venden, que también he hecho videos por ahí, eh, de algunos bootcamps que con un par de meses ya salís listo. Porque, ¿qué hacen esos bootcamps? Te meten toda la información en 8 o 10 horas de estudio y terminás quemado y no terminás de asimilar todos los conceptos. Pues imagínate que tenés que practicar cada cosa. Lleva tiempo, lleva tiempo. Bueno, esto lo vamos a dejar por acá. Después voy a terminar de ver esos dos videos de que me faltan de... Bueno, que son árboles binarios. Pero bueno, lo voy a estar viendo, calculo que mañana. Sí, mañana. Bueno, me voy a ir yendo. Em, Gracias por pasar a los que pasaron, los que comentaron. Y nada, cualquier cosa abajo están mis redes. Me pueden contactar por ahí, cualquier cosa. Em, y nada, nos vemos en el próximo stream. Calculo que mañana a la mañana. Así que nada, un saludo y nos estamos viendo.